Okay, so the topic of my presentation today is the advances in geotechnical evaluations applied to tailings dams. I work at the AECOM Denver office. Here in Denver, we oversee a lot of tailings dam facilities in the US and overseas, and also some projects related to water retention dams. Enjoyed AECOM 4 years ago, and since then I've been basically spending most of my time evaluating tailings dams in the west part and also in the southwest part of the United States. Um, the overview of my presentation, we're going to first start with an introduction of the problem that we face nowadays in terms of how we evaluate these tailings facilities. The second one is to look at the material behavior of the tailings in terms of fundamental soil mechanics, along with some laboratory testing, some in situ testing that we can look at, and how we can assess the behavior in terms of volumetric behavior, how pore pressures develop, how volume change develop during shear, and how we can connect this type of behavior into a more holistic framework so that we can extrapolate behavior once we analyze specific situations. And for that, we're going to use a couple of case histories that will help us evaluate our material behavior, in which previously we have characterized that based on laboratory testing, in situ testing. So the case histories use numerical evaluations. For these cases, we use finite differences modeling. And those numerical modeling help us at the end of the day to judge our current understanding of the material behavior, how we can evaluate our sites in a boundary value problem approach. Lastly, I'm going to give some summary of the main aspects of this presentation. So first, introduction. Most of us might have seen this video that happened in Brazil. This is the Feijão or the Brumadinho dam that failed, which unfortunately caused more than 200 deaths after the failure. So you can see a very abrupt failure that basically takes the majority of the portion of the dam, and this failure unfortunately was not expected, in a sense that monitoring didn't give enough warning of it. There's some discussion of small movement prior to this failure, and some other recent investigation are actually talking about some of the drilling inducing steady liquefaction and specific locations of this case history. However, there's still more work to be done to really understand what happened. If it was merely static due to loss of bonding a long time with subsequent raining event, or was it like the trigger was a drilling process during operation? The type of failure mechanisms we have in these dams, we're going to describe that in terms of stress path. Is a very well-known plot that we deal with in soil mechanics. The typical, let's say, soft soil or clay type of failure that we learn in soil mechanics is the undrained shear contracting material, whereby we increase the shear stresses of the soil. Say we're building an embankment over subsoil, therefore we generate excess pore pressures because the permeability of the overlaying foundation is low enough so it cannot dissipate pore pressures. There's a point in which we pass the material in a stability line for a given void ratio or state, up to what point then we decrease the shear stresses or the shear strength up to the critical state. This is a very idealistic stress path. Obviously, in the field, we're going to have some other aspects in the behavior of these contracting materials. For example, we have lateral extrusion, we have constant shear drain path, or we have a more stable stress path, for example, the undrained shear dilative material, in which we generate excess pore pressures that are negative, therefore we increase the mean effective stress, and therefore we increase the shear strength of the material. Other contractive or unloading stress path, as we can see, are fully drained up to the moment of instability. Once we pass the instability line, then there is sufficient volumetric strains that develop in the soil, and since the onset of instability is rapidly, then the transition becomes immediate into undrained conditions. One example of this, number 3, could be the rising of the phreatic surface, which is slow enough to still make a drain type of path. So there's not really excess pore pressure that we measured. However, once we hit the instability line, we transition into a more unstable behavior that could be undrained. These are static type of stress path. We have also dynamic loading stress path like liquefaction triggering that we have seen all over again in loose saturated granules type of materials. However, loose tailings materials, CLT materials that we typically find in the field are also liquefiable, especially if they're contractive and loose enough. How do we evaluate this tailings material? How do we characterize the material behavior? Just to touch on briefly on the behavior or volumetric behavior of soils, we understand this behavior in terms of volumetric, so volume change under shear. For example, contractive materials will accumulate volumetric change, or will decrease its volume, therefore will have some compression for loose sands or for loose type of granular materials. Whereas dense sands initially will have some level of contraction, however, at large strains, the change in volume will tend to be dilative. Therefore, there's not enough space for a dense sand to keep contracted. So therefore, the particles will try to ride over each other, and therefore will create a net negative volume. Therefore, it's considered dilation. This is under drain conditions. However, if we restrict volume change during testing, let's say in a triaxial testing on the direct impulse shear test, instead of having a change in volume, we will have a volumetric response in terms of pore water pressures. Therefore, loose samples will tend to generate positive pore pressures, whereas dense samples will tend to generate negative excess pore pressures. That's the volumetric behavior. The volumetric behavior is also very tied to the shear behavior that we have. Therefore, based on our evaluations, we can have both brittle and ductile materials. Typically, we find brittle response at both low and high confining pressures. For certain type of materials, as we increase our confining pressures, the behavior will be more ductile in general. But there are some materials that we can find that even though you are at high confining pressures, they still exhibit some brittleness. The most common, I guess, behavior that we have in the field, and based on the recent case histories, is the brittleness elucidates at low confining pressure. This is more typical, but it doesn't negate that we can find a material that could be sensitive at high confining pressure. So it's really material dependent, and that's why it's important when you looked at your tailings really to figure out what type of material do we have, what void ratio would you have in your facility, and how it varies with confining pressure. As we will know, these materials or these structures keep growing and growing as we deposit the tailings. Therefore, the range of stresses increases with time. So we need to continuously evaluate the behavior of these materials. This is a very interesting flowchart that basically will guide us in how to evaluate the behavior of the materials. We first start in the field because most of these tailings are very difficult to sample. So we really pay attention into the in situ behavior. For that, we first start with the CPT behavior. With the CPT, as we went along, we measure pore pressures. Based on the pore pressure, we can see if the material is contractive or dilative. We also looked at the soil behavior type. What are we talking about? Clay contractive material? Are we talking about sandy? Are we talking about intermediate material? So the first step is to perform your CPT evaluation. Then we're going to judge if the material is dilative or contractive. Some tailings are interbedded, so you can find both materials at the same time or with depth. You may find some good material. If it's an underflow, for example, sandy compacted material, you may find that your CPT is going to suggest that it's dilative with negative excess pore pressure. And depending on what you find in the field, then you're going to focus more on the laboratory testing evaluation to pay attention to particular type of behavior that you may find in the field. If it's dilative, we judge it as a ductile and unstable. Therefore, if you perform laboratory testing, typically you will have a strain hardening behavior. We also do some stress path based on cyclic triaxial tests, the DSS test. We evaluate the critical state behavior. We also perform post-cyclic behavior to see if the material will lose strength with after cyclic loading. Similarly, for the brittle ductile evaluation is the most critical aspect of these tailings, because this is the material that will give us issues. The material that will drop in strength very fast at very small percentage of strains, if we identify it that way. So then to identify a material that will be sensitive or will be prone, for example, to static liquefaction, then we perform laboratory testing. We perform laboratory bench shear tests. We can perform also field bench shear tests. We perform monotonic cyclic triaxial testing, anisotropically or isotropically consolidated. We perform direct simple shear test. And after we characterize the material with laboratory and field in terms of its stress strain response, then we can look at how brittle is this material, right? If it's only brittle under one test, if it's brittle under all test conditions, if it's brittle also in cyclic loading, under post-cyclic loading. So all of these aspects will help us understand and really assess the sensitivity of this material. Once we characterize our material based on the laboratory testing and in situ testing, we give them a final characterization. Our material can be brittle, which could be subject to flow liquefaction if your initial static shear stresses are high enough compared to the residual or your liquefied shear strength ratio, or it could be ductile, in which your material will have sufficient strain, will mobilize sufficient strength to basically accumulate strength without losing significant strength. And based on these two behaviors, we characterize our strength for each type of tailings. For example, this is two distinct type of tailings. The left-hand side shows the underflow sand, in which we show the tip resistance and the soil behavior type. For example, we can see that typically this is a material that have a high tip resistance between 50 to 100 TSF. We can see that the material is mostly sand-like. It could be an underflow, compacted, probably. And in the right-hand side, we can see a more interbedded type of tailings. Initially, we have probably an underflow sand, and then we have a fine tailings material in which we have an isolation between the tip resistances as well. We have an intercalation between high tip resistances, low tip resistances that suggests probably more like a clay type of material here, sandy here, and silty in the middle. And the characterization based on I sub C, which is the soil behavior index, it's above 2.6, which tells us that in average this soil is a clay or behave like a clay. So tailings can have both behaviors, sands and clay. And in terms of dynamic pore pressures that we measure in the CPT, so we have our tip resistance, we measure also the lip friction, but one important addition of this measurement is the dynamic pore pressure. and also the what we call static pore pressure after dissipation at the specific points. So it's really performing a test, as we the tip penetrate these materials. So materials that exhibit higher dynamic pore pressure than the original hydrostatic or the pressure at equilibrium will be judged as contractive because it generates pore pressure, so there's a tendency for volume change, but since the penetration is fast enough, then as a response, the tailings generate pore pressures. Similarly, there could be some materials that are dilative and at specific location, and you can see the dynamic pore pressure tends to generate negative excess pore pressure below our hydrostatic condition or our equilibrium condition, and therefore we can have dilative materials as well. These three charts are derived from work that Professor Robertson and Schneider did. Basically, what you plot here in the y-axis, the normalized resistance is, then we have in the x-axis a normalized friction ratio. This is an example in which for a given tailings we plot this, and what is interesting that to judge our tailings for a screening level approach, we can, this is two versions, this is a 2010 and 2016, but essentially what is plotted on top is that flow failure case histories that happen not only in tailings but also in sandy materials. And it's a way of telling you pay attention to this material because it's plotting near or on top of case histories that have failed. So that gives an idea on how loose is a material or how can behave under undrained loading conditions. For example, we also have estimates that Professor Robertson laid out in terms of state parameters. So materials that has state parameters less than -0.05 will be judged as dilative, and then we will have that for this given tailings we have a dilative material. If our material were plotted nearby here, then it will be judged as contractive material. And the sensitivity, you will have to do more studies in terms of laboratory testing or in situ testing to really understand the sensitivity of this material. But this is a screening level approach in which it can really easily tell you right away which materials you need to pay attention to. The updated version divides this in terms of behavior. For example, S is sand, and then the C is contractive and D is dilative. So for higher tip resistances, we transition our behavior from contractive to dilative, and for higher friction ratios, we transition our material type from sandy to a more like clay-like material, having a lot of transition soils here. You may realize that when you plot tailings, it's not idealistic clay or sands, depending on where you are. For example, you are in the middle between your impoundment or your starter dike, you may find that you have a lot of transitional materials. And that might not be that evident in this type of plots, but once you plot pore pressures in terms of U2, which is the ratio between the excess pore pressure divided or normalized by the initial effective stress, you sometimes find that the data point will plot in the transitional soils. And that makes sense if you look at the permeable hydraulic conductivities of these tailings, so they basically are in between sands and clays, and then you will have some material that will plot in the C sub C area. However, once you look at pore pressures, because of the intermediate nature of these tailings, you will have materials that will plot in the T sub C, which is transitional contractive. So pay attention to those things. I think those are important when you want to characterize your tailings in terms of behavior. In terms of CPT, at the end of the day, what you want to have as an end product is your tip resistance and estimate of your state parameter that comes from correlations, in this case, Plus method. We also have your pore pressure difference that will help you also assess if it's contractive or dilative. Some correlations for liquefaction potential based on ozone, peak and range shear strength, residual strength, and the index that is important to assess the sensitivity as a screening level approach is the Brittle Index, which is the ratio between the peak and range shear strength and the residual strength. Then if you have shear wave velocities, you can also plot it. For this case, we didn't have it, and also you can estimate your effective friction angle. So we're going to look in more detail about what characterization can we have based on lab testing for this brittle material. We can see two types of behavior, and this is based on lab testing performed in tailings. You can see the collapse brittle behavior, in which you really have a sudden drop in strength or a loss of strength at a small percentage of value of actual strains. However, some tailings take more strain to actually decrease value in the shear stresses. For example, here we hit the peak and rapidly have a decrease in the shear stresses at around 1% or so. However, here you still are at 10% and you're still increasing your shear stresses. So there's a different characteristic of these tailings. So one is collapse brittle, who have a sudden drop in the strength. However, the strain softening or more ductile in a sense will take strength to get to a residual condition. These are better tailings in terms of behavior. However, to characterize the unresidual or the liquefied shear strength sometimes is difficult because of the range of strains that we expect those values to be. So the type of materials that we are interested in is, okay, are we seeing brittle behavior? Are we seeing strain softening behavior? Are we seeing strain hardening? And then we have to quantify this reduction in shear stresses. For example, here, the shear stresses is in the order of 4 psi. However, the residual strength is less than a half of psi. So our sensitivity is much larger than 8 in this case. In this case, for a given, for example, 20%, you may find that your sensitivity is less than 1.2 or 1.5. So a significant difference in sensitivity that you compute from lab testing. There are other testing that we can do to assess the sensitivity. There's the laboratory bench shear test that we can also measure the sensitivity of this tailings material. We have the field bench shear test. Unfortunately, the field bench shear test, you have to really play around with the rotation rate, because if you sometimes rotate it at the rotation rate that the standard tells you, you are not going to reach undrained conditions. Therefore, instead of measuring your undrained shear strength, you will measure your partially drained or drained strength. And typically, that's higher values than what you expect. So in some cases, you have to go a little bit outside of the range of the code and really, test different rate of rotations to really see the drop in strength that you expect in these fine-grained tailings. Some other testing is done with a monotonic direct simple shear test, in which you take different cycles and there are strain control tests, and you can see the drop in the maximum peak stresses. And that also gives you an idea of the sensitivity. So this is not something new. In fact, it has been studied for the last 60 years. I'm here showing a couple of examples from Gonzalo Castro. If you recall, Gonzalo was Dr. Casagrande's student at Harvard. So the top two plots shows sandy type of materials, and the top bottom is what I show in terms of tailings. So the same behavior. For example, for a high sensitivity liquefiable type of sandy materials, you will see that initially under stress control triaxial testing, you increase your shear stresses. It takes about 18 minutes, but suddenly at the point of yielding or instability, then these stresses are basically lost in a fraction of seconds. However, a more ductile material, low sensitivity sand will get to the peak, but the shear stresses are lost in a minute or so. So different type of material, same for sands and clay. So you want to really pay attention to the level of sensitivity you have. And for that, we define the sensitivity ratio, which is just the ratio between the peak shear stress and also the residual shear stresses. And you can have, for example, values that vary all over the place, anywhere from 1 up to 80 for highly sensitive marine clays. Oh, when we looked at laboratory testing, we really want to also pay attention to the stress path, pore pressures, and stress strain. In terms of stress path, when we looked at contractive behavior, we can see the development of positive excess pore pressure. The shear stress relatively decreases with strain up to the failure line. In terms of the dilative behavior, we can see that initially the response could be contractive. However, at larger strains, this material will tend to dilate, therefore will generate negative excess pore pressure, and the shear stresses will increase with shear strains up to the failure envelope. Now, once we have all our database from our tailings, we want to look at reduce the data in terms of critical state behavior and brittleness index. For that, we typically use our knowledge in critical state soil mechanics to reduce the information we have from triaxial testing. Then we looked at for that at CIU and CID tests to come up with our critical state line. And based on that, we can judge if specific tests are contractive, are dilative, and that's basically depending on how the initial void ratio or the state parameter, as defined by Jefferson Bean, sit with the critical state line for a specific tailings material. And based on that state parameter, you can also tie this to the brittleness index and look at for potential for rapid stress loss. Some reference for this type of analysis, we have Jefferson Bean, the second edition book is a good one to use, and then Robertson 2019, in which he talks about the potential for brittleness as we increase our stresses. In terms of critical state soil mechanics, is a framework that helps you tie that volumetric response into the initial state, and that's how we relate our strength to your peak and your residual underage shear strength. This concept had origins in the 1900s based on the dam that the U.S. Army Corps of Engineers. In that project, they used shear buck tests to come up with the response as a function of the void ratio. Then subsequent work from the Cambridge School and the Harvard School further explored these critical state soil mechanics, in which the three main contributions was we have a unique critical state line for a given confining pressure. We can have a critical void ratio, and therefore you can construct a critical state line that will describe if your material is contractive or dilative. If your initial void ratio are above this line, then you will see that your material is contractive, and if it's below, you will see that your material is dilative. To measure this critical state line, we use triaxial testing. You will find that it's very sensitive to gradation, so pay attention to your variability that you have, especially for intermediate tailings. They're typically flat at low stresses, which is very tied to the K-history range that we observe from the field failures. And as we increase in our stresses, the slope of your critical state line can change. So it's really project specific, and we cannot really take one critical state line from one project and use it for a different project. So you really have to do testing to come up with your laboratory-based critical state line. These are examples for critical state line. The left one is for underflow mine tailings, and then this one is for the natural sand to US sand, both from Castro and Verdugo. One aspect that I wanted to discuss here is that you can use either undrained testing, you can use drain testing to come up with this critical state line. You need to pay attention to your volumetric response to see if you have reached critical state condition. And you can use different type of sample preparation, compacted, slurry, moist damping, variations of your preparation might not have an impact in your critical state line, because the critical state line is not really fabric dependent. This is an example of a critical state line defined by CIU testing, and this is the estimate of the state parameters for this specific site, based on CPT, based on in situ density measurements, based on consolidation tests. And what you see is that all your in situ void ratios for this specific material are telling you that you are below your critical state line. Therefore, your material will behave as dilative at large values of shear strains. So this material will tend to behave ductile at higher stresses. It's analog to what happens to heat and cold. Other type of materials, the intermediate type of tailings, you may realize that you don't have a unique critical state line, but you will have different critical state line depending on gradation. Some sandy materials will tend to blood in the right side, some low plasticity silts will tend to blow in the left hand side. So you have to really look at your gradation, look at your index test when you look at the whole picture in terms of stress response, volumetric response, and your critical state line. This is an example of how we relate your state parameter, your compressibility of this critical state line with your shear, under shear strength for the peak and the residual. And that basically controls your residual. And the ratio between the peak and your residual controls what we call the Brittle Index. So as we increase our state parameter, or as we increase our initial stress ratio, which is also a distance for a given point in the stress void ratio space to the critical state, we will increase our brittleness. Similar for the state parameter compressibility. As we increase our state parameter, if we decrease our compressibility, then our brittleness increases. So there are many literature that you can take a look. This is are a few of them, but essentially what these different references tell you is that you can use your CPT measurements to estimate an in situ state parameter, and you have to come up with a relationship between your state parameter and your tip resistance for your given soil. So this can also be tailored for your specific project. So then you can use subsequent CPT's readings to basically come up with a distribution of state parameters in your sections and do your further evaluations. In terms of cyclic and post-cyclic behavior, we have the same thing. We can see that loose tailings tend to develop positive pore pressures that actually reach a liquefaction, level ground liquefaction of Ru nearly 1. And you can see that the stress strain curve tends to get bigger and bigger, accumulate more strains, and eventually liquefy at high value of Ru. And you see the shear strain number of cycles plot that there's a point in which the transition between a slow rate of shear strain gain and a fast or shear strain development that tells us that this is essentially a liquefiable soil. And that happens not necessarily an Ru of 1, but could happen even before a level of Ru nearly 0.8 or so. We typically, after this cyclic testing, we do post-cycling, and we can see that some of them are dilative, and it doesn't mean that the material is great. It just means that we have reached probably critical state conditions for our low confining pressures, and then it will dilate into your critical state line or point. In cyclic testing, we can see ductile behavior in which we can have significant number of cycles to accumulate shear strain, and those were state parameters negative than minus 0.05, but we can have also brittle behavior during cyclic loading. So everything that we do in laboratory testing has to be reduced in terms of state parameter and compressibility to really understand pore pressures, to really understand sensitivity, to really understand shear strain accumulation in cyclic loading. Looking at aspects that are secondary but still important are the multidirectional loading. This is some tests performed for Ottawa sand that BOMIC 2018 performed, And what you see is that if you include the other directional of movement on top of the unidirectional to make the stress strain or the strain path circular or figure 8, you will have a more tendency for compaction. Therefore, you may generate more pore pressures under undrain loading or more compaction in drain loading. If we tie together the static and the cyclic behavior, you may find that you can have a monotonic test that goes through the peak and then goes to the residual critical state. You have the same relative density, but instead of reaching to the critical state line monotonically, you can reach that cyclically as well. You can see that initially it contracts, then second cycles generates excess pore pressures, and then once you are in the nearly zero effective stretch, you perform a monotonic test, and then you dilate into your critical state line, therefore reducing your excess pore pressures, as we can see here. So this behavior, monotonic and cyclic, can also be explained in terms of critical state theory. Once we have strain softening materials, the issue is that these materials will tend to generate progressive failure, in which you initially fail one portion of the dam, and since you increase your shear stresses in the back portion of the dam, then your shear strains are going to increase, your shear stress are going to increase, and these stresses get transferred between each other, and we have what we call progressive failure. And for that, as I mentioned, we looked at, in summary, for potential of strain softening, we looked at laboratory testing, we look at in situ testing, Bayesian test is an important one, DSS, CAU, and we looked at the stress strain curve from both, and we can really estimate our sensitivity levels for our tailings. These are examples of Bayesian tests that we have done for certain materials. You can see some normalized shear stresses that are really high, and again, this might be affected for partial drainage, so we really need to understand what values we expect. In summary, what the purpose of the material evaluation is to understand if our material will be subject to a rapid strength loss, which is worrisome for us because our site or our dam could be subject to static liquefaction. If our material is not, if it's dilated, then we're not to worry about it. Under cyclic loading, you can still have significant deformations, but nonetheless, you won't have a rapid loss of strength, and you won't have a flow failure. If we characterize any tailings in our site as brittle, then that should raise our alarm. We should design safety measures to actually restrict the amount of movement that these structures may have under these conditions. And really, in terms of design, you should use a precautionary design in which you should assume that these materials will trigger regardless of the trigger mechanism, and then design a buttress or something that can hold these materials in the event of liquefaction. To finish the presentation, I wanted to do a quick overview of a couple of case histories. The first one is a static failure. The second one is a dynamic type of response under an earthquake for a tailing facility. And the importance of these couple of case histories to evaluate the performance of these tailings over time. As I mentioned, these tailings are built over many years, so they really change in nature. They could be changing the position, they could be changing energy dissipation along the structure. There could be, for example, a dam crossing during impoundment. There could be some restrictions in how in spacing. Therefore, you have to, instead of increasing your dam laterally, you have to increase it up, and that typically induces more shear stress in your dam. You have seepage conditions, you have some foundations that are not very well drained, so you have a very, very different aspects, not only in your site, but also during the life of your dam. For example, this stress path basically tells you what conditions you can have. You can have If you cut, for example, on a slope, you may be reducing your shear stresses, but you also may be reducing your effective stresses. Really, looking at the stress path will help you understand at what rate you decrease your mean effective stresses with respect to your shear stresses, and really judge if you are improving or making it worse when you excavate something. In terms of pore pressures, it's important to measure that with piezometers. There are some more advanced tensiometers in which you can measure saturation. You can see, for example, here for this specific site, initially this specific point had low level of saturation in terms of strength. That means that our material will be very competent, but there's a point in which the pond of the tailings got closer, and then we resaturate, some contract the whole tailings, and then the risk of liquefaction can happen. So it's really important to measure our level of saturation in our dam, because those really change with the life of the dam. For that, we use laboratory testing. We use seismic data, for example, shear wave velocity and P wave velocities. We use tensiometers. We use Shelby tooth estimate of saturations. We use CVTs, and then we have to idealize our pore pressure response to see which materials is saturated or not. And the materials that are saturated, we can have some of them could be subject to a contractive behavior. They develop positive pore pressure, or some of them could be ductile too. So really the evaluation of the saturation is important. We talked about strength softening, and for this specific case history that I want to talk about, we have a material that is a strength softening, and for this case we model that in staging using a numerical model built in finite difference tool. Then we use a numerical model called PM4 Sealed, in which you can change your different backbone curve, you can change the softening rate, and basically try to predict the instability that happens in the field. And for that, we could capture the instability not only in terms of pore pressures, but also in terms of deformations. So you can see here the initial deformations with time were minor up to the onset of yielding, in which the rate of deformations increases exponentially. So you can do this type of analysis to come up with your trigger mechanism. There are other analyses in which you already know that the case history trigger. However, you're interested in more your runout analysis, how much your flow mass will travel. So this type of MPM analysis or material point methods will help you guide that type of evaluations that you need. In terms of seismic, we recently published this paper in the Tailings and Mine Waste Conference. We had a tailings facility in the west part of the United States that was subject to a magnitude 5.7 earthquake. Fortunately, we had a lot of measurements. We have a lot of instrumentation in the facility, pore pressure transducer. We had accelerometers in the rock and the top of the tailings and the free field. We have inclinometers, so we really have a lot of information to calibrate our numerical models and analyze the behavior of these tailings. This is the main shock shown as a yellow circle, and all the red ones are the aftershocks. You can see here the different inclinometer response that we saw after the earthquake. Really transitional type of movement for this fine tailings material. However, back in the impoundment, when you have saturated low confining pressure material, you have this typical volcano that tells us that there's some liquefaction going on. However, this type of behavior was only superficial, didn't compromise the facility of the dam. And in order to evaluate liquefaction under cyclic conditions, then we have to really look at the coupled model, in which we model the stress strain cyclic behavior. We model the stress path due to the pore pressure generation, the recyclic loading, and also we model the modulus reduction and damping curve, which is important to understand the level of amplification that we have. And those are confining pressure dependent, And once we have our model, we have to compare with our measurements. For this specific case history, we have an earthquake, and we have different values of RU measuring, before the earthquake and after the earthquake. And we simulated that in our couple models using finite difference methods. And we came up with reasonable values in terms of excess pore pressures, in which our couple PM4 model simulations were in line to what we recorded in the field. In terms of movements, we can see that our couple models also predicted the level of displacement consistent with what we had from INSAR. Obviously, INSAR is a lot of judgment in terms of how we analyze the different satellites, if the orientation, but in the ballpark we were right on in terms of modeling. So this type of case history will help you guide your understanding of your material, and really depends on your level of strains. For this case, it was small to moderate level of strain, but it will help you guide your small strain shear moduli and the level of nonlinearity for cases that you may have static liquefaction. So as a summary, I have the following. The evaluations are based on multi-stage approach. You have to look at your laboratory testing, your in situ testing. You have to look at your case histories if you have those to really evaluate your numerical modeling, right? Because you really want to have confidence that your constitutive models that you use in your dynamic deformation analysis are basically calibrated with your case histories, calibrated with laboratory testing. And that's basically the end goal of these evaluations, to be able to use these calibrated models to analyze unforeseen scenarios, or different dam heights that may happen 10 or 20 years from now. As the last comment, the static liquefaction and draining stability are a fundamental concern with this type of structure, especially if we have a brittle type of behavior. So really, it's very difficult to monitor these dams against failure. So you should assume that any triggering mechanism will happen, and be careful with your observational approach, because that won't work in this type of dams that have these brittle materials. With that, I thank you for attending this presentation, and I will be happy to take questions via email. Thank you all, and have a good day.